So what we want to do is evaluate the reactivity of our Grignard. And that's ultimately what the question's pushing. Okay? So why do we have to use an aprotic solvent with our Grignard as opposed to protic solvent? Okay? So let's look at the reactivity of our Grignard. Okay? Do you see any positives and negatives?
There's the ionic bond.
We have an ionic bond through a lot of that. Okay? Probably the more important ionic bond would be the one between the carbon and the magnesium. Wow, it's really different upside down. So we've got that bond being ionic. Where those electrons spend most of their time? The carbon or with the magnesium?
No, I don't know.
What's the difference between carbon and magnesium?
Carbon has more valence electrons. It's more electronegative.
I like that answer a lot better. It's more electronegative. It does not have more valence electrons. Magnesium, or not more valence, more electrons. The magnesium has more electrons. It's bigger. Okay. But carbon is much more electronegative than magnesium. So where would the electrons in that bond spend most of their time?
Carbon.
In the carbon. Let's see if I can do this. This is going to look awful. Okay. So what we could go through and do is, instead of looking at it as we just did, wow. We've got our that's a benzene ring. We've got a lone pair of electrons. This is awful. Sorry, I'm redrawing that. You have to look at it upside down. Oh. We've got that carbon with the negative charge. Right? So that's what's reacting. Okay? Problem with negative charges. What species, what kinds of reactions or reactants can we get that have negative charge? So this would be back to our 6 primary definitions. We've got our Bronsted-Lowry acids and bases, and our Lewis acids and bases. Okay? Which of those have negative or have extra electrons?
Lewis base.
Yep. Our Lewis base is typically negative. Anything else?
And
So we see you pointing at Bronsted base. What is your definition for a Bronsted base?
proton acceptor.
What's the charge on a proton?
Positive.
So what charge would a base need to be to react with the positive?
Negative.
There's our other negative. So if we see negative, we should immediately be thinking Bronsted-Lowry base and Lewis base. Okay? In a Grignard reaction, we want the carbon to act as a nucleophile, which is the same thing as a Lewis base. Okay? For it to act as a Bronsted-Lowry base, it must react with a proton, a positively charged hydrogen. Okay? In a Grignard reaction, we don't want to see that. So what we're going to do is prevent H plus from showing up. Okay? So H plus is ultimately a bad thing. I'm going to show it with a partial positive charge. Okay? How can we get H plus? What kind of compound would give you an H plus?
Protic.
If we attach an electronegative element, say like oxygen. Okay? We now have what is known as a protic species, because that oxygen takes the electrons away from the hydrogen, giving us that partial positive. Okay? If we go back to our solvent definitions, if we have a protic solvent, we've generated H+, which means H+ interacts with the negative. What does our Grignard react as?
The nucleophile.
What does the Grignard react it with? If the hydrogen reacts with the positive hydrogen, meaning we get the Bronsted-Lowry base. We want it to act as the nucleophile, not the base. So what we have to do is make sure we limit the exposure to protons. Does that make sense?